All right, let's get started. Okay, so today we are going to be talking about CMOS transistors. This is actually the fundamental building blocks, right, that underlie all the digital systems these days. So this is also one of the few lectures where we try to venture slightly below the gate level digital abstraction. Okay, so this is one of the few lectures that we do that. The goal here is to give you guys a simplified but intuitive view of how we actually build these logic gates using these transistors. Okay, and actually, one lecture, this is a very rich topic, right? That deserves the full course. Okay, one lecture will not do justice on CMOS, but our goal here is to stay at the digital abstraction level, right? And hopefully, this is something that will give you some intuition behind some of the costs, right? And we have been talking about simplification of logic function, right? So hopefully this lecture will give you some idea of, right, how many transistors do we need to implement some of those gates. All right. Somehow my pointer is not working. Is it working? Okay. The slide is not moving. All right. Okay, good. Okay, so just a couple announcements. I know some of you are already asking questions about labs, right? So we'll be starting the lab sessions next week. Okay. The first lab is fairly straightforward, right? You guys just need to turn in and submit MOS assignment, right, on CMS. If you have questions about those assignment, right, you can either go to the lab sessions or TA office hours, but you can also go to the lab sessions to check off this quarters installation, right? So hopefully the first lab will not take too long, right? If you have already checked off your lab, right, quarters part, you don't even have to go there, right? You've already finished the first lab, right? And also, I know the due date is on Tuesday, right? So make sure that you turn in the first four, I remember, the assignments, right, on Tuesday. In case some of you need more time to install quarters, will allow you to check off the quarters part, okay, on Wednesday, right, the Wednesday lab. We'll make an announcement on that as well. Also, I've been getting some questions about prelims, right? On the website, we list that the prelims will be in class. I just want to make it clear that actually all the exams, first the prelims, will be on Zoom, right? Since this class is entirely virtualized. So we'll figure out a way to do it, and we'll give you more instruction information in early March, 2 weeks before exam. Okay. All right, so before we talk about CMOS, let me introduce two more interesting gates, and these are also very important gates. First one is called a NAND gate. So look at the name, right? It's basically a negation of the AND. Okay, basically we insert inverter on the opposite side of the AND gate. That's it. So we call it NAND, and this is the symbol, right? Over here, and just pay attention to this bubble, right? So the moment we have a bubble, that means we are doing some inversion. Okay, in this case, we are inverting the opposite. And actually, we can apply De Morgan's law, right? So this is something that we have learned, right, in lecture 2. Okay. Turns out this is also a NAND gate, right? You just look at how De Morgan's law works here, right? So basically, if you invert both inputs for OR gate over here, okay, so this is also a NAND, right? So in this class, in most cases, right? So in most cases, we'll be using this symbol, right, to indicate a NAND. But this is also fine, right? Because these two are functionally equivalent due to De Morgan. Okay. So we think about truth table for NAND. How many ones do we have in the output column? Alma, you're trying to say something? Right?
Oh, I wasn't sure. I was going to say 3. I was saying to myself.
Right, 3, right? Because if you think about AND gate, right? So we have 3 zeros, right? And this is the inversion. So we have 3 ones. Okay, the cool thing about NAND gate is that we can actually build all kinds of circuits, any circuits, using NAND only. Okay, so this is so-called universal gate. Let me just try to convince you that. Okay, this is pretty cool, right? This is pretty remarkable. Okay, so we can actually use NAND to build a NOT gate. So how does this work? Okay, this is the symbol for NAND, right? Okay, now we actually have two inputs, right? Inversion, right? Inverter or NOT gate has one input. So what do we do with the other input? Let's say one input is X. So how do we get X prime here? Any ideas? Okay. All right. So Momo is sitting, right? Also Nusha, right? So so you guys are already getting good answers. Let me just explain this, right? So one idea is that we put a 1 here, right? So this is basically saying that this is also inverter, right? So what theorem are we using here? Identity, right? Okay, we can just put a 1, right, as the other input, or okay, we can just tie these two inputs, right? This is X and this is X prime. It's basically saying this is also true, right? Which theorem are we using here? Which theorem? Okay, the theorem that we hopefully come to love, right? In the previous lecture, idempotency, right? Okay, so that's how we build a NOT gate, right? Using NAND. How about AND? Again, you want to build NAND out of build AND out of NAND. Okay, it's very straightforward, right? So yeah, some of you already got the idea, right? We are just missing an inverter, right, on the output side, and we already know how to build this inverter using NAND, right? Okay, so we can build NAND, right, out of AND out of NAND as well. Okay, how about OR gate? What do we do? Yes, so just check out the chat window, right? There are already very good ideas, right? On chat window, so we invert those input, right? Right? Okay. So what is this? Right, this is basically X naught plus Y naught, and we take another inversion. This is what? This is basically, sorry, I should have. This really is AND, right? This is X plus Y, right? According to the model. Make sense? All right, so this is a universal gate, right? We can basically use NAND gate to build these 3 primitive gates. So let me use another way to convince you, right? Last time is also a recap of what we covered last time, right? So last time we talked about 2-level logic, right? So in this case, we have SOP, right? Sum of products, right? We have something called sum plane, right? The level, this first level is a sum, the second level, this is really this level is a sum, right? This level is product, right? Okay, the sum of product. We can represent any combination logic, right, using 2-level logic form, right? And turns out that we can do a small trick, right? So if you look at all of these signals or wires, right? So let's say for each signal, we invert it twice. Okay, so the same thing, right? According to involution, right? The theorem. Don't worry too much about this symbol, right? Actually, this inverter, you guys already familiar with this, right? This is actually sort of an inverted buffer, but this is actually also inverter. Okay. Later on in one of the lectures, we may see this symbol again, but don't worry too much about this. These are basically 2 inverters. Okay. Same thing, right? If you agree on that, right? So then everything else, right, becomes very obvious, right? So just look at the shaded areas, right? So we only have NAND, right? We only need NAND gates in the shaded areas. Make sense? Right? We just talk about, right? NAND is inverter after AND, right? On the output side, or we can just invert all the inputs for OR gate. That's also a NAND, right? That's another way to understand why NAND is interesting, right? It's a universal gate. Any questions? Not? Okay, so this is NAND gate, right? We'll look at it again. Right, so something else is also interesting. It's called NOR gate. Okay, so this is basically OR plus an inverter. Right, this is a symbol that we use in most cases. And again, according to De Morgan, we can also use this form, right, which is corresponding to this symbol, right? Very much similar to the NAND gate, right? So the NOR gate, we can also use right, these are two symbols. So we can either invert the output side for OR gate or invert the input side for AND gate. All right, so actually not surprisingly, NOR gate is also a universal gate. Okay, we can pretty much create anything, right? Any conditional logic, any gates, just using NOR. I'm not going to repeat the same exercise for NOT, AND, and OR, but let me just remind you again about this this concept, right? POS, product of sum. This is another two-level form that we covered last time, right? So basically, we have an OR plane and the first level, and the AND, right? Product sums. So same trick, right? You know, we can just for each one of the signals, right? These are actually wires. If you just insert two inverters to break this wire, okay, invert it twice, we get the same signal, right? And if you just look at the shaded areas, so we only have NOR gates, okay, at both levels. All right. Okay, so you guys may wonder, right? So why are we doing this, right? So why do we go through this trouble, right? So why do we want to convert something that's so simple, right? Like OR and AND, right, into NAND or NOR? That's going to be very clear later on in this lecture, right? Actually, we can implement NAND and NOR in a very efficient way using CMOS transistors. Okay. All right. Okay, so let's talk about CMOS, right? Let's talk about transistors. First, a little bit of a history, right? Actually, the transistor was invented by these three gentlemen, right? Three scientists, okay, Bellas, John Bardeen, Walter Bratton, and William Shockley. Okay, and all three won the Nobel Prize in physics later on, right, for this contribution. And in 1950s, right? So Jack Kilby and Robert Noyce, they actually independently figure out a way to integrate more than one transistors in a single device. Of course, later we know that this is silicon, right? This turned out to be a huge deal as well, right? So that means we can actually put later on we can put many transistors, right, on a single piece of silicon. And of course, right, so this is also Nobel Prize worthy, and Jack Kilby also won the Nobel Prize later on. And Robert Noyce, so this is also a very important person. Okay, actually, the textbook dedicated a sidebar for this person, right? Robert Noyce. Okay, he actually co-founded the Intel with Gordon Moore. Robert Noyce also deserved Nobel Prize, but unfortunately, he actually passed away too early. Okay, unfortunately. And this guy, right? This name must ring a bell, right? To many of you, right? There's something called Moore's Law, right? It's basically, something that's observed by Gordon Moore. Okay. Basically, Gordon Moore in 1965, I believe, right, published this article. So it's actually not a law. Okay. So this is something interesting, right, to know, something important to remember. It's really not a law. It's more of observation. It's more of a prediction. Okay. It just happened that this prediction turns out to be, somewhat like a self-fulfilling prophecy. Okay. Because this entire industry, right, is going after this, right? So trying to make this alive, right? What exactly is the Moore's Law? So initially, Gordon Moore is saying that the number of transistor count, based on the transistor count on a single chip. Okay, that's why you look at this table. Okay, this is some of the early generation of Intel processors. Okay, you look at the transistor count, right? The basic number of transistors we can integrate on a single device, on a single chip. It's going to double every year. That's Gordon Moore's prediction. But later on, he made some correction. He's saying that maybe it's 2 years, right? Doubling every 2 years. And later on, there are other some corrections, so 18 months, and now it's actually slowed down a little bit more. Okay, but it's pretty much a self-fulfilling prophecy, like I said, right? Because there's so much capital, right? So much manpower being put into this industry to keep Moore's law alive, okay? Because it's just so important, right? And we may talk about that maybe in one of the lectures when we cover the advanced topic, right? So what's going on with Moore's law, right? Is it still alive, right? What's the implication such, right? But for now, let's look at the first early days. Okay, right. So some of you are already curious enough, right? You guys are reading my mind. Okay, wait until the next slide, right? So some are asking like, how many transistors do you have in the latest chip? Okay, right. But look at the old chips, right? So we start with something pretty small, right? Although it's actually not too small, right? 2,000 transistors. Back then, it's not right. It's not a small deal. And in about 20 years later, right? So people are able to integrate about 1 million transistors. Okay, on single chip. And actually back then, right? So there's something called the technology process, right? So this is basically sort of indication of the size of the transistor. Okay, back then it's like 0.8 micron. Okay, but you look at the this some of the latest technology. This is the curve. This is a chart from TSMC. TSMC is the foundry in Taiwan, right? So actually, most of the chips these days are produced by TSMC. Okay. Intel also has their own foundry, okay. But like for example, the iPhone chips, right? These GPUs, all of the FPGAs, right? The ones that you're going to be using, they're produced by TSMC. Okay, this is the curve they're showing, and see here. Right now we are at 5 nanometer technology node. Okay, just to give you guys a sense, to give you guys some perspective, the thickness of the human hair is around 0.1 millimeter. Okay, so that's about, I think, 100,000x, right, thicker than this, this nanometer scale transistor. Okay, just want to give you guys a sense. All right, how impressive this thing is, right? So really, people, this industry has advanced and figure out very advanced fabrication technology. These days, fabricating these chips are just like printing newspapers, okay, but on a piece of silicon. Okay, so some people are asking, right? Yeah, I guess you guys are already Googled, right? But let me show you some chips, right? Some representative chips. I think these are all fabricated at TSMC. First one is the Apple chip. So this one's used in iPhone 11. Remember that in the first lecture, I showed you guys sort of old device, right? The first generation of iPad. I already told you that, in that device, right? So we have 1 billion transistors. Okay. In this newer one, right? They are actually now integrated 8 billion transistors. Okay, so this is a mobile chip, right? This is actually usually a smaller chip, right? That's packed in your mobile device, okay? Cell phone or tablets, right? Next one is a server class CPU. It's not from Intel. Intel has its own fabrication facility, right? This is from AMD. Okay, this is a multi-core CPU processor, right? This one has close to 40 billion transistors. All right. Any guess what's the next one? Next one is, of course, larger. We just talk mobile CPU, server class CPU. Any guess what's the next one? It's actually something called GPU. Okay, I don't know how many of you have heard about GPU. So this is a chip from NVIDIA. Okay, so this is actually the chip that people are using these days to train, this deep learning, deep neural network models, because we need so much compute power. Okay, right. So this is actually not the largest chip anymore. These are just some of the published number that I can find. Believe it or not, this is some startup company is trying to even try to put this so-called wafer scale computing. I might explain that concept again in a later lecture, maybe in one topic, right? So actually trying to put like more than 1 trillion transistors on a single device. just to tackle the challenge of this kind of deep learning training. Okay, right. So this is very impressive, right? 50 billion transistor. Okay, but what exactly is a transistor? Right. Again, we'll just sort of take a peek, right, slightly below the digital abstraction. So this is not something that you guys need to, really remember, right? So, but there's actually a book chapter, right, so that you can read, so to understand more about the underlying principle, operating principle of the so-called MOS transistor. So we're talking about CMOS, right? MOS transistor CMOS. But first, let's talk about what is a MOS and MOS, right? So MOS really stand for, this is a long name: metal oxide, right? Semiconductor field effect transistors. Really the first thing, that's the first thing: metal oxide and semiconductor. These are the three kind of materials that are required for us to build a transistor. Okay. So we usually use metal for something called gate, right? And then below the gate, we have oxide so that we can build a capacitor. And we need semiconductor so we can control, how the current flows, basically. And we can turn it on and off, right, based on this so-called field effect. This is really based on, this electric field. Okay, again, I'm not going to get into the detail of how this actually works. Okay, so this deserves a course, like I mentioned. Okay, this is a very rich topic, but if you guys are interested, check out the book chapter. But all you need to remember in this class, okay, is this is a so-called three-terminal device, this transistor. So we have something called gate and source and drain. Okay. And this transistor can be acting like a switch. Okay, this is basically like a switch, right? We talk a lot about switch, right? It's basically inherent digital, right? Switch 0, 1. So by manipulating the voltage, so this is a voltage controlled switch. Okay, so by manipulating voltage on this gate, right? So if this switch is closed or turned on, okay, then we will have current, okay, flowing through source or drain, either from source to drain or drain to source. Okay, that's basically the intuition. It's basically a voltage control switch. And if it's off, okay, you can just think of it as something that has a very high resistance, right? So with a resistance of infinity. So basically this thing is open, the switch is open. If it's closed, then we can think of it as something with very low resistance. Okay. All right. Okay. This is basically, the most basic concept behind transistors, right? Just remember that this is a three-terminal device and it's controlled by a gate. And it's called MOS. This is for short. We usually just call it MOS. Okay. All right. So then this is just another wheel, right? This wheel will be this one. So we'll be using this wheel more often. This is a more abstract wheel. Okay. One more time, we have three terminals. Okay. The input is usually connected to the gate, right? So look at how the source and drain are connected. Prism. This is basically a switch. All right. Okay. Oh, so there are actually some questions that I missed. Okay. We were talking about some of the latest chips, right? Right. I believe that most of the chips that I showed you guys are using 7 nanometer technology. Okay. Either 7 or some of them might be at a slightly older technology now, like 12 or 14. Okay. All right. So let's see how we actually build something useful out of the switches, right? So first, let's look at something that we are very familiar with, NOT gate, right? We're familiar with the notion of the 0, 1, the truth table. So in this lecture, since I'm using 0, 1, so I want to indicate the voltage level. So I'm going to use L and H. Okay, L means low voltage level, H means high voltage level. That's it, right? And we can of course make it even more concrete, right? So let's say high means 5 volt, right? Low means 0 volt. Okay, it's the same truth table, right? Just want to clarify the terms. And of course, when the input voltage is low, right? So we want output to be high, right? So we want output to be connected to a voltage supply. Okay, we're going to be seeing this pretty soon. So we'll be using VDD, okay, in this lecture to indicate voltage supply. So this indicates high voltage, right? So when input voltage is high, right, is the inverter, right, the output is going to be low, right? So we want the output to be connected to the ground. Ground is low voltage. Okay, right? So we use GND to indicate ground. Okay, so these are the some of the terms that we are going to be using. All right, so let's see how we can actually build a NOT gate using switches. In fact, right, so we are going to be using two kinds of switches. Okay, and these two types of switches are complementary, okay, for each other, to each other. First, we have a so-called type 1 switch. Okay, later on, we will replace type 1 switch with the actual MOS transistor. First, for type 1 switch, it closes when the input is 0. It opens. Closes means it's conducting. Okay, the current is flowing through. The current is flowing through the switch. Okay, that's what I mean by closed. When it's open, it means it's not conducting. Okay, so it's switched off. So for type 1 switch, right? So it's closed when input is 0 or low, and open when input is 1 or high. And type 2 is the opposite. It's closed when input is 1 and open when input is 0. Okay, and it turns out that we only need 2 switches to build this NOT gate. Right? So we use type 1 switch to connect. Okay, so this type 1 switch is connected to high voltage or VDD. Okay. Type 2 switch is connected to the ground. Okay, and this is a voltage control switch, right? This 3-terminal device. Okay, one terminal is connected to the switch, to VDD. The other terminal is connected to the input. Right? This is the input. Right? So these are the connection. Right? Just want to make it clear. These are connection. So the input, okay, is actually connected to both gates. So we call it gates, right? 3-terminal device, both switches. All right. So first, when input is low, or 0, okay. See here, right? So the type 1 switch is closed, right? It's closed. So that means, so this path is conducting, right? So we have a path over here, right? From the high voltage VDD to the output side, right? Output is here. So that's where output will be driven high. Make sense? Right? Input is low, output is high. Okay. And if we change this one, the input to H, high, okay, and this switch will be open. Okay, basically this will not be conducting anymore, but this switch will be closed. The type 2 switch will be closed. So that's where we have a path, right? That's connecting the output to the ground. Okay, that means the output will be driven low. The output will become L. Any questions about this? This is basically doing inversion, right? And these two switches are complementary to each other, right? Like I mentioned, okay, meaning that they have opposite behavior, right? So let me ask you guys a question. At any given time, how many switches on? Just one, right? And exactly one. They cannot be both closed. Why? If they're both closed, what do we have? It's designed that way. So we have short circuit, right? So if both of these switches are conducting, then we have a direct path from VDD to ground. That means short circuit. That means the current will be very high, right? Because we assume that these switches have a low resistance, okay? And the current will be very high, and it's going to burn the whole thing. Okay? And it's designed that way. It's complementary. At any given time, one switch will be on, one switch will be off. So there's no direct path between VDD and ground. Okay, so if you understand this one, you pretty much understand, right? So how we'll be able to build NOR gate using a CMOS transistor. So let's see, how exactly do we do that? Actually, there are two kinds of MOS transistors. One is called PMOS. Okay. It's basically the type 1 switch, okay, which will be on or closed when the input or the gate has a low voltage. Right? It's on when the input is low. And we also have a type 2 switch filled with NMOS. Okay, it's another kind of transistor, NMOS. If you look at the symbol here, okay, it's the opposite, right? So with NMOS, it's gonna be on or closed. So when the gate, right, is tied to a high voltage input. That's it, right? And one more time, right? So it's important to understand the notation here, right? The symbol here, when we have a bubble, right? When we have bubble, it really means, usually means this is a active low, right? So basically this is going to be on when we have a 0. That's where we put the bubble. It's active low. Okay. We can look at the textbook, right? So there, you can understand, right, what exactly is P and N, right? So how we do the doping, how we can dope a semiconductor to create this kind of behavior. But again, this is outside the scope of this lecture, okay? And also you'll be not tested on that book chapter. And in general, I think there are some questions on Piazza, right, asking about how to take notes and such. So if you understand the lecture materials well enough, okay, you should be able to do well in the homework and exams. Okay, the book chapters are going to be helpful for you to understand the lecture materials. Okay. All right. So this is NMOS and PMOS. Okay. Any questions about this too? Okay, the behavior and such. Okay. If not, let's look at, right? So why do we need both of them? Okay. Actually, these two are complementary to each other, right? So first, their behaviors are sort of opposite, right, to each other. One closes when input is low, the other closes when input is high, right? And the other important thing is, so actually PMOS can pass a good 1, okay, but the poor 0, okay? And NMOS is good at passing 0, but not 1. Okay, so that's why we actually need both of them. If you actually want to understand why this is the case, okay, check out this link. Okay? Again, this is not a required reading, but if you're curious enough to understand why this is the case, right, just go to this link. Okay, so it's really about actually there's something called the threshold, right? So threshold voltage, VTH. Okay, so for each transistor, and whether the transistor is on or off really depends on the voltage difference between the gate and the source. Okay, if the difference between the gate and source is beyond the threshold, then this thing is on. Okay, but it turns out that this threshold will also plays a role, okay, when you pass 1 or 0. Okay, for a PMOS transistor, okay, it can actually pass a perfect 1, but it can only pass a 0, which is near the threshold voltage, okay, but not 0. It's near the threshold voltage, VTH. That's why we usually do not use it to pass 0 for PMOS. Then we only use NMOS to do that, but we use PMOS to pass 1. Okay, so these are complementary. Also, this complementary to C is really where the CMOS comes from. Okay, C remains complementary. Okay, we have been talking about the behavior of these two kind of transistors. Let's look at how we actually build things, right, using them. I just talked about CMOS, right? So CMOS really means complementary MOS. This is actually the kind of device that we use, okay, in most of the digital system these days. So these transistors, right, the type of transistor dominate the market. And we actually need both of them. Okay, we both need both NMOS and PMOS, right? So we usually create a network. We call it over here. So I'm gonna okay. We usually create a network using PMOS transistor. Okay, so which is connected to the VDD, right? This is so-called the pull up network. It's called put up network because we are putting the output to 1. See here, we use P here because P can possibly do 1. And we use NMOS network over here, which is connected to the ground to pass 0. Okay, we want to put down the output to 0. So NMOS can pass it with 0. So that's why we want to use both of them. And the things that we cover in this lecture, something called static CMOS gate. We are not going to be talking about other dynamic CMOS gates. The book has, I think, a small section covering that. Feel free to look at it. It's outside the scope. Okay, so basically everything that we cover is so-called static CMOS gate. Okay. All right. Okay, so let's see if there's any questions. I was asking, does PMOS just invert 0 input? You can just invert 1 input. Sort of, yes, right? So the way we use it, but let's look at some concrete examples. Okay. All right, so things have been fairly abstract so far, right? So let's look at the inverter again. Okay. And I'll also quiz you about the behavior of these CMOS and NMOS, right? And PMOS. Okay, so make sure you ask questions in case you do not follow this example. All right, so this is how we draw inverter using PMOS and NMOS. Okay, so these combined are called CMOS. This is a CMOS inverter. Right. So we have a single input A, right, which is connected to both gates. Right. So this is gate for PMOS. This is a gate for NMOS. Okay. We will name both transistors. NMOS is Q1. We name PMOS as Q2. This is the output. Okay. Output Z. We also have VDD, and this is ground. Right. Just want to make sure that you guys are familiar with this kind of diagram. This is a CMOS diagram. Abstract diagram though. Okay, so let me ask you, when A is high, which transistor is on? Q1 or Q2? Q1, right? Q1 is on. Okay, Q1 is on. Very good, right? So that's where Q2 is off. That's where Z is 0, right? Because there's this connection. So this path is conducting, right, from Z to ground. Z, the level of Z, voltage level of Z is driven to 0. Okay, so that's where we are inverting. And when A is low, Q2 is on, right? Q1 is off. Again, if you're not really, you don't want to memorize things, right? So in this class, in general, we don't want to memorize things. We just need to understand the notion, right? These are the notations, right? So bubble means this is active low. Right? Bubble usually means active low. Right? If you have bubble, this means this thing's on, right? Then you have a 0. Okay, this is PMOS. Okay, so we just talked about this, right? And this is inverter, right? That's it. And one more time, so only one of the transistors are on, right? It's on at any given time. Any questions? If not, let's look at another one. Okay. This is slightly more complex, right? So, for inverter, we only use 2 transistors, right? In this case, now we have 4 transistors, right? 2 PMOS, 2 NMOS, right? So NMOS, PMOS in static CMOS always comes in pairs. Okay, we always have 2 N, right? If N is, right, in this case, for this gate, right? So we have 2 inputs, right? So we have 4 in this case, right? We have 4 transistors. Okay, so also want to note the notation here, right? Okay, again, so we are naming these transistors, right? Q1 and Q2. In this case, the reason we put them together is because they are both driven by A, right? So look at the connection. So Q1 and Q2, they're both connected to A. All right. So let's try to reason right? This a bit, right? Before we review the output column. Okay, some of you probably have already guessed, right? What exactly is going on here? But look at this input combination first, right? When A and B, they're both lows. What do we have? Okay, so which network is conducting? We have PMOS network, right? Right, this is PMOS network, and we have NMOS network, right? Then both of them are low. Which one is conducting? The VDD one, right? So one connected to the VDD, right? So that's the PMOS part, right? Okay, because both Q2, see here, both Q2 and Q4, right? Right. See here, we have this parallel structure, right? So we will emphasize a lot, right, on this structure later on. Okay, so parallel structure, both Q2 and Q4, they are conducting, right? They are close. So of course, we have a path, right, from VD to Z. So do we need both of Q2 and Q4 to be on to have paths from VD to Z? No, right? So with the parallel structure, we only need one of them, right? Only one of this Q2 or Q4 needs to be on. Make sense, right? So that's parallel structure. But let's look at over here. Okay, so this is NMOS. This is something that we'll see pretty often. Okay, later on, so we'll see this duality, right? So when we have a parallel structure in PMOS, we have something called the series structure. So these two are put in serial, right? Okay, so they are stacked together in NMOS. When A and B, let's look at this row, right? When A is high, B is low. Okay, which transistor is on? Q1 is on, right? But not Q3. So that means this path is not conducting, right? For a series structure, we need both of this to be on. Make sense? Okay. All right. So that's that. Let's just fill out the output column, right? I'm not gonna. This is basically like an expanded version of truth table, right? So later on, when you guys try to reason about this kind of CMOS network, you can try to expand the truth table like this, right? Try to write down the on and off, right, status for each transistor. But in many cases, it's not really necessary. But let's just look at the output column, right? When both A and B are L, right, low, what is Z? Just tell me, right? High, right? Okay, for a quiz later on, I'm gonna ask you to enter high and low, okay? Not 0, 1, so make sure to do that. And LH, high or low? Also high, right? HL, same thing, right? Okay, because one of these transistors, like one of the PMOS transistors is on, okay? Then the rest is not important, right? So if PMOS network is on, then you know for sure NMOS network is off, vice versa. Okay, we just talked about HH, right? So when both of the A and B are both high, okay, the NMOS network's on, PMOS network is off. So that's where we have a low. What is this gate? Now that you guys see the truth table, this is a NAND, right? This is a NAND. we can build a NAND, 2-input NAND, using just 4 transistors. It's very efficient. Okay. All right, so this is NAND. Okay. All right, so if you have a question, make sure you ask, right? A quiz is going to come up pretty soon. Just a heads up. Okay. And we can actually further expand this, right? So we talk about 2-input NAND, 2-input NAND, and this is how the 3-input NAND looks like. Hopefully you guys see the beauty of this, right? Okay, this is, all you need to do is to add one more transistor in the P network, in the parallel structure of the PMOS network, and then you stack one more transistor, right? NMOS transistor in the NMOS network. You get a 3-input NAND. Okay. Again, I'm not gonna go through the expanded truth table. If you guys have any doubts, right, just go through this. Okay, so there's a question. So why? Let's see. Okay, I guess you guys are asking about this one, right? All right. So the question is, explain why L goes to high, right? This one, right? Okay. Again, we have A being L, right? B being L, right? So this is a PMOS. We have bubble here. It means active low, active low. Okay. So that means this path is on. This path is also on, right? Then we have a direct path. We have connected path from VDD to Z. That's where Z is going to be driven high. Make sense? Okay. And let's see, there are quite a few good questions, right? So, and Amanda is asking, how do you know how to tell high versus low for Z? Okay, right. Okay, good question, right? So whether Z is high or low, it really depends on whether, the PMOS network is on or NMOS network is on, right? So basically whether you're connecting to the ground or VDD. If the PMOS network is on, right? If Q2 or Q4 is on, so we are connecting to VDD. That's where Z is high, right? VDD means high. Otherwise, the NMOS network is on, okay? The one in the bottom, right? So this, I keep saying this word, right? Because I really want you guys to remember, this is something you want to remember, right? The name, NMOS, PMOS, right? This is NMOS, okay? So if this path is on, right? Then Z is connected to the ground. Ground means low voltage. Okay, and we can have different structures, right? So this is a very simple structure. We can have series structure in PMOS network. We can also have parallel structure in NMOS network. Okay, we'll see more examples. Okay, right. So let's maybe go through one more example, right? So this is a 3-input NAND, right? In this case, right, given n inputs, we have 2 N transistors, right? Okay, so before we do the quiz, okay, actually the quiz is about this gate. Okay, I'm going to ask you about this gate, but before we do that, let's do some exercises. So I just want to make sure that you guys are following. Okay. All right. So this is mystery gate, right? You already know the answer. Don't type it. Okay. The quiz about this. Okay. All right. So let's look at this gate, right? So this is actually related to someone's question, right? See here, the structure is different, actually opposite to the previous one, right? We have series structure for the PMOS network. We have parallel structure for the NMOS network, right? So this is a difference. Again, for each input, it's connected to both NMOS and PMOS. So let's look at HH, right? When both A and B are high. Okay, so let's just fill in the status for each transistor. Q1, on or off? On, right? Okay, right? This is NMOS. NMOS is active when the input is high. Okay, Q2 over here. On or off? Off. Very good. Q3 over here. on, right? Q4 off, right? Okay. So what is Z? Which part is conducting? Which part is connected? PMOS or NMOS? Right. This is off, off, on, on. Okay, NMOS, right? So this one, very good, right? So the bottom network, right? The lower part, right? The NMOS network is conducting. It's called a pull-down network. Pull-down means we are pulling down the voltage of Z. Okay? We have the current is flowing like this. Okay, current is flowing from Z to the ground. So that's where Z is what? High or low? Low. Okay, good. Any questions before we do the quiz? Maybe let's do one more. HL. Just tell me about Z. HL. A is H, B is L. Okay, which network is conducting? So see here, right? So it's quick answer, right? Is right NMOS still, right? But just look at this, right? So which transistor is on? Oh, here. Q2 is off, right? Because it's high. A is high. This guy's on, right? Because B is low. But since this is in series, so this whole path is off, right? The PMOS network is off. So that means the Z is still low, right? NMOS network, very good, right? NMOS network is conducting, and Z is low.